So the next question is 3. A gas at 2 atmospheric pressure and a temperature of 200 degrees is first expanded isothermally until its volume has doubled. It then undergoes an isobaric compression until it returns to its original volume. First, show this process on a PV diagram and then find the final temperature in Celsius and the pressure. So let's draw the PV diagram firstly. PV. As there said, gas was expanded isothermally. Isothermally means temperature will be constant. So here will be just like this line, and until its volume has doubled. It means here will be initial volume, let's call it V0, and here will be 2V0, right? Doubled then initial its value. It then undergoes an isobaric compression until it returns to its original volume. Isobaric compression means pressure will be constant, and the compression means volume is decreasing. So we draw this. So until it returns to original volume, we draw this. So here, firstly, here number of pressure will be was the 2 atmospheric pressure, right? And we need to find this P final. So how will we find this pressure? Firstly, we need to write the equation for isothermal process. So here will be P0 V0 equal to P1 and V1, right? Here, P0 equal to 2 atmospheric, 2 times 10 to the power of 5. V0 will be unknown, it's a number, but here will be cancelled. P1, it is this value unknown that we need to find. P1, let's call it P final, and the V1 is here. V1 equal to 2V0. So here V0 will be cancelled and final pressure equal to 2 times 10 to the power of 5 over 2 equal to 10 to the power of 5 Pascal, or we can say it's 1 atmospheric pressure. It means here equal to 1 atmospheric pressure. And we need to find the final temperature. The final temperature in this point, right? T final. Let's go. In this final process is isobaric process. Let's write the equation for isobaric process. Here will be V over T will be constant, right? We need to write it here as this V0 T0 over V1 over T1, right? Here V1 is equal to 2V0 over T0. T0 is this here and here temperature will be constant. It's equal to 200 degrees. Let's write it here, 200 degrees. equal to V1. V1, it's final volume here. It's equal to V0 over T1. T1, it's final temperature here, T1. So all these values are given. V0 will be cancelled. T1 equal to T0 over 2. T0 to 100 degree, and we will convert it to the Kelvin. Here will be 473 Kelvin. 473 over 2 equal to approximately 236.5 Kelvin. And we need to convert it in Celsius. In Celsius will be here, right? 273 236.5 minus 273, right? So here will be minus 36.5 degree in Celsius. So this is the answers for the third question. We found the P final before, and we found the final temperature. Let's turn on the next question. For containers A and B in figure hold the same gas. The volume of B is 4 times the volume of A. The two containers are connected by a thin tube, negligible volume, and a valve that is closed. The gas is at a 300 Kelvin and pressure of 1 atmospheric, right? The gas in B is at 400 Kelvin and pressure 5 atmospheric pressure. Heaters will maintain the temperatures of A and B even after the valve is opened. After the valve is opened, the gas will flow one way or the other until A and B have equal pressure. What is this final pressure? We need to find the pressure in this valve after opening this valve. So firstly, what do we do? We need to find the number of moles in every containers, right? Let's find that in A, the first container. We knew that ideal gas law, PV equal to nRT. So in this equation, we can find the number of moles. PV over RT, right? Here, A container, VA container, over TA. So here, pressure and temperature are given. So we can write it here, 10 to the power of 5 times V A over, let's write it R, just by letter, because then will be here R will be cancelled because it's constant value, and the TA is equal to 300. So here will be approximately 333. Let's write it. This our volume is not given, and the R will be cancelled. Let's find the second containers. PB VB over RTB. So here 5 times VB, volume in the B container. They're said that the volume of B is 4 times the volume of A. It means here will be 4 times VA, right? Over R times TB is equal to 400 Kelvin. So here will be 5,000 VA over R. So we found each of the containers number of moles. So let's find the number of moles after valve is opened. Now we knew that a number of moles will be equal, right? NAB. Let's call it NA. This by this. It's number of moles of a container after the valve is opened. And also here, B is equal to initially a number of moles, right? And B. It means, let's add these numbers. Here will be 5,333.3 VA over R. So this is the number of moles after the valve is opened, right? So what do we do? The next is pressure. Pressure will be equal of A and the B, because here written that after the valve is opened, gas will flow one way or the other until A and B have equal pressure. It means valve is opening. When the valve is opened, pressure will be equal. So let's call it PA like this, equal to PB. This is the valve pressure of the valve after is opening. So let's write here equation of the pressure equal to nRT to the A container. Here will be also NA over VA, right? Equal to NB RTB over VB. So here we can find the let's find the one of this number of moles after valve is opening. Let's find the number of moles of the A container. So here will be R will be also cancelled. Here only volume A times NB times TB over TA times VB, right? So here all these values are given also. NB times VA times TB is equal to 400, right? 400 divided by 300 Kelvin, and times VB is equal to 4 VA. So here will be also cancelled, right? Here will be 100. So after this, NP times 100 over 300, right? Here also zeros are cancelled, and then it means here NA equal to NB over 3, right? So here 3NA equal to NB. So we found the expression for the this number of moles. Now let's put it this equation here to the first to the first equation. So here number of moles of the two container after valve is opened equal to, as we found before, 5,333.3 times VA over R, right? We found it here, equal to NA plus NB, right? After number of moles of the B container after valve is opened equal to 3 times of NA. It means here will be 4 NA. So here we can find the NA easily, right? So let's write the result of calculation. Here will be 1,333.3 VA over R. So we found the number of moles for the A container after valve is opened. So we can put it here. PA and PB equal. So if we find the pressure of the A container, it will be equal to the container pressure of the B container. So we know that it's equation from the ideal gas equation, RT over VA. So NA equal to this, and we put it here. So there will be R's will be cancelled, V volume will be also cancelled. So here will be let's write the result of calculation because here will be only this number and the temperature. So here will be approximately 400,000 Pascal. So answer is this for the fourth question. So we found the pressure for the A container, it's equal to pressure of the B container. So let's turn on to the next question. It is 5. Fifth question is an insulated jar containing 200 grams of solid candle wax is placed on a hot plate that supplies heat energy to the wax at the rate of 220 joule over a second. The wax temperature is measured every 30 seconds, yielding the following data. Here we'll given the data. And what are the specific heat of the solid wax? The melting point and the wax is heat of fusion. So firstly, we need to find the specific heat. Specific heat means this number, right? C. So we know that equation for the heat equal to Cm delta T, right? For solids, increasing temperature or decreasing. formula of heat is this. So here we can find the C, Q over M delta T, right? Delta T is change of temperature, not time. So Q, let's find the sum of this times. I will find to this time from 0 to 30. It means every second heat supplies 200 joule, and in 30 seconds is unknown. So X equal to 6,600 joule. This heat was supplied to increase its temperature from 20 to 31.7. So let's write it here. Mass is equal to 200 gram is equal to 0.2 kilogram times delta T. It's change of the temperature. It's 11.7 is equal to approximately 2,900 joule over kilogram times Kelvin. Right? So now we found the first question. Let's find the next question. Next question is melting point. Melting point is when the solid starts to melt. Right? We can find it here logically. How we can find here, as we see in the table, two of this temperature are constant for 30 seconds. During 30 seconds, temperature was constant. Temperature was not changing. It means when the solid reach the melting point, then solid's temperature will be constant for some times. So it means the melting point of this solid wax is equal to 70.5 degree Celsius. So we found the melting point, and we need to find the wax heat of fusion. Heat of fusion, we can find it by this formula: fusion times mass, right? L fusion equal to Q over mass. Q is heat, right? When the solid will start to melting. So how much heat was supplied to reach the melting point, to reach melt to this solid. As we see here, to reach the melting point, melting temperature 70.5 was time used that to reach this temperature was 180 seconds. So we need to find the 180 seconds heat in 180 seconds. So we knew that here 1 second was supplied to 120 joule and 180 x joule. Simple proportion, x equal to 39,600 joule. So we put it here. Over mass equal to 0.2. So here will be, let's write the result of calculation, approximately 200,000 joule over kilogram. This is the number heat of fusion.